This is lesson 2.4 about differentiability and continuity. So a little review of how we determine about things being continuous, and then also talking about how we know something is differentiable, which means that you can find the derivatives. So that's what we're going to talk about today. So connecting this is really important. So we talked about theorems before, where like the intermediate value theorem, where the very first thing we have to do is state the function is continuous, because the theorem is only relevant if the function is continuous. So we have different ways to determine continuity. We also are going to have some theorems that say, okay, this theorem is true if this thing is differentiable and continuous, and things like that. So that's one of the other reasons we'll need to determine that. Well, one huge thing has to do with us being able to determine if something is differentiable. And if we know it's differentiable, then we know it's continuous. That's going to be a big deal because continuity is important. So we say that a function is differentiable at a specific point, x equals c, if and only if these two limits exist and they are L, which is a finite value, so you can't get infinity. And these two limits are simply from the left and from the right, the derivatives, because this is that alternative form of the definition of derivatives. So basically what we're saying is you have to be able to find these two limits, and they have to be the same. If that's the case, then we say the function is differentiable at that point. If and only if you'll remember back from geometry, that's logic that just says this is true both ways. If a function is differentiable at a point x equals c, then these two limits will be equal. Also true that if the two limits are equal and equal a finite value, the function is differentiable. So that's what if and only if means. It means it's true both directions. Okay, so now we're going to look at some ways that a derivative fails to exist so that we can understand why those things have to be true. And then those are going to be ways that we look and immediately know, okay, there's not going to be a derivative because there's either a corner, a cusp, a vertical tangent, or a discontinuity. Okay, so we're going to see what those look like. All right, so if we look at the derivative for the function y equals absolute value of x minus 1, then we want to talk about what that shows us, okay? So absolute value of x minus 1, I don't know why that says sketch the slope graph, so that's not what we're doing. So we're just doing what is the derivative as x approaches negative 1. So this graph right here is f of x equals absolute value of x minus 1. Remember that absolute value of x is a v, the minus 1 is on the inside, so this thing has been shifted to the right 1, okay? So what is f prime of x as x approaches 1 from the left? Okay, so remember that when we are approaching from the left of 1 and asking the derivative, we're saying, what's the derivative as I come towards 1 from the left? So, well, the graph looks like this on the left side of 1. So the derivative is going to be the slope of that line, and that slope is negative 1. So the f prime on the left side is negative 1. F prime on the right side, which is part B, so that's the slope of this line, is going to be positive 1. Is f continuous at x equals 1? Well, that answer is yes. There is a point there. It's continuous. Then the next question is f differentiable at x equals 1? And the answer is no. So while it is continuous there is no derivative because the left derivative and right derivatives are not the same, okay? So the limit of the derivative from the left and the derivative from the right do not equal each other, okay? So like if we wanted to give a reason, which you need to learn to do all the time, we would go ahead and write since, and we have to give the math reason. since x approaching 1 from the left of f prime, so that's the limit we just found, the limit of the slope does not equal the limit as x approaches 1 from the right of the derivative. Okay, so in other words, derivative on the left, derivative on the right, not the same. So therefore, it's not differentiable there. Okay, but it is continuous. There is a point there. Okay, next one. Here's the graph of third root of x. So we're going to use the alternative form of the derivative to show that the function must have a vertical tangent line there. Okay? So the alternative form of the derivative is to find the limit as x goes to 0 of f of x minus f of 0. Well, if you plug in 0 to the function f here, you're just going to get 0. And that is going to be over x minus 0, the thing that we're dividing by, or the thing we're going to. X is going to 0. So that's going to give me the limit as x goes to 0 of the third root of x, which I'm going to write as x to the 1/3 over x to the first, which is going to be, if we simplify that, you have x to the 1/3 over x to the first, so you're going to get 1 over x to the 2/3, because you're going to take 3/3 or 1/3 minus 3/3, or there's 3/3 in the bottom, subtract 1/3, your answer stays in the bottom, so that's supposed to be a 2/3. That's kind of hard to see. Okay, now if I do that limit as x goes to 0, you're going to get 1 over 0, which is undefined. Okay, so the limit is undefined. Okay, that limit is undefined. So therefore we have a vertical tangent line. Because remember that the derivative is the slope of the tangent line, and we got a slope that was undefined. So we have a vertical tangent line there. And you can see it. Look at the graph. You can see what's going to happen there. If I were to draw a bunch of tangent lines and just keep getting closer and closer and closer till I'm at the center, I'm going to eventually have to be straight up and down right here. Same thing if I come from this side. My lines are just going to keep turning until they have to be straight up and down right at 0. Okay, so you have a vertical tangent line. So you still have a continuous function, you still have a point there, but you don't have a derivative at x equals 0. Okay? All right, let's look at 3. So here we have a graph of 1 over x plus 2 whole thing squared. So let's talk about the derivative as x approaches 2 from the left and from the right. Okay? So as x approaches negative 2 from the right, okay, so as I come to negative 2 from the right, derivative is slopes of tangent lines. So look at these tangent lines. What are they doing? What are they approaching? Well, they're approaching, the derivative is approaching infinity. The slope of the tangent line is getting steeper and steeper and steeper, and it's actually negative infinity because they're actually negative sloped if you look at the bottom one. So the bottom one shows you the negative, and they're just going to keep being negative, but they're just going to get super steep. And then if you go on the other side, as x approaches negative 2 from the left, so when I'm on this side, same thing. Now I have positive slope, it just gets bigger and bigger and bigger as I keep going up. And so f prime of x is going to approach positive infinity. Okay? And so that would mean that f is not differentiable at x equals 2. And the reason for that is, again, the limit from the left and the limit from the right of the derivatives have to equal a number. And they have to be the same number. They equaled infinity, so we do not have that. So f is not differentiable at x equals negative 2. And then in this example, x is also not continuous at negative 2. You have a vertical asymptote there. Now, let's look at part B, which is the same function, but now they're telling you the derivative. So they're saying, hey, I'm telling you that the derivative of the function f is negative 2 over x plus 2 whole thing cubed. So now it says what would happen if we could evaluate f prime at -2. So this thing is the derivative of this graph, okay, of that function. And now they're saying, let's take that formula then and let's evaluate -2. Well, if I try to do that, I'm going to get undefined. Again, right? Because I'm going to be dividing by 0. So it's also undefined. So therefore, we have no derivative there. Okay? All right. So something that's super important, and this is like huge. Definitely box this in because we're going to use this quite often. So remember, we have a theorem currently, intermediate value theorem, that requires a function to be continuous. Well, they may not tell you a function is continuous, but they might tell you a function is differentiable. So they might say, hey, here's this function and it's differentiable at a specific point, or it's differentiable everywhere. You can then imply that f must be continuous, okay? So this theorem is only true in this direction. So if f is differentiable, then you know f must be continuous. Now that's not actually that hard to think about. Differentiable means it has a derivative. The derivative is the slope of a tangent line. If there's a slope of a tangent line that does exist, then there must be a point there. You can't have a tangent line there if there wasn't a point there. Okay, so it's kind of easy to think through this. So if you're told something's differentiable, then you definitely know it's continuous. Okay, so that's what number 1 says. Differentiability implies continuity. But it is absolutely possible, hence the first 2 examples, it is possible for a function to be continuous, like this one was at x equals 1, and this one at x equals 0. They're continuous there, but they are not differentiable. Okay, so continuity does not imply differentiability. It's possible that the derivative exists, but not necessarily the case. These are your typical reasons for something to be not differentiable. You have a sharp corner, that's where segments come together. A cusp, that's where curves come together to a point, or a vertical tangent line. All of those reasons will be reasons that we don't have differentiability, and then also a discontinuity would be a reason also. Of course, if it's not continuous, we can't have, obviously we don't have a tangent line there because there's no point there. So if there's not a point there, if it's discontinuous, we can't have a tangent line. Okay, so back to geometry again, okay? So you studied if-then statements. Those are just called if-then statements. So if a function is differentiable, then the function is continuous. That's the if-then statement. The converse is when you switch the if and the then. The inverse is when you negate them but leave them in the same order. And then the contrapositive, which is what it wants us to write, is when you switch the order of the 2 statements and negate them both. The contrapositive and the original statement have the same truth value. So this is a theorem, this is true. It's true in this direction, which means when I write the contrapositive, it is also true, okay? So the contrapositive is if a function is not continuous, because that's the then part of the original statement, okay, at x equals c. So I switch if and then, and I negate it. So I put not. If it's not continuous at x equals c, then the function is not differentiable. So that is also a true statement. Okay? So that's the contrapositive. So the contrapositive switches the if and then and negates them both. And the easiest way to negate is often just to say not. Okay? So if a function is differentiable, then it's continuous. It's the same truth as if a function is not continuous, then it's not differentiable. Okay? So be cautious with your logic. Make sure you follow that. Okay, so let's describe the values here at where the function is differentiable here for this function. So when we look at the picture, we should be able to see that right here and right here, it is not going to be differentiable because it is continuous there, but you have what we call a cusp there. That's where, or a sharp corner. I usually call it a cusp because you have curves coming into a sharp point. I consider a corner when you have segments that come together, okay? So it's not going to be differentiable there. So we need to figure out if we want to describe where the function is differentiable, we need to find out where those two values are, and then we can't use them. So that means we need to solve when does x squared minus 5 equal 0, okay? So this is a quadratic. Every quadratic can be solved by factoring, and if that doesn't work, you can use the quadratic formula. There's also sort of an exception. I don't have the x term. So the easier way to solve this would be to move the 5 over, and you have x squared equals 5, and you use the square root property. There are two roots, plus and minus the square root of 5. Probably one of the most missed things in calculus is a lot of you would say, oh, the answer is x equals square root of 5. But there are two roots, plus and minus. Also look at the picture. If you look at the graph, you can see you've got a plus and a minus. So my answer is, and always answer the question, we would say g of x is continuous on, when you give intervals, you say on, so it is continuous on. So I'm going to be minus infinity to negative square root of 5, union negative square root of 5 to positive square root of 5, which I don't need to put the positive, union square root of 5 to infinity. Okay, because when we give those values, we always say where the x values are. Okay, so I'm going left to right and answering that question. So we need to answer it. That's where it's continuous. Okay, so let's look at example 4, which I think in your paper maybe says example 5. But look for this example with these words in it. So find all values for where the function is differentiable. Okay, so this is a piecewise function. So think about this again. So this function is going to be differentiable. So let's look at each piece. So the top piece is a parabola. We're only doing it for part of the way, but we know that a parabola is going to have a derivative everywhere. The second piece is a line. A line is going to have a derivative everywhere. The last piece is a parabola. A parabola is going to have a derivative everywhere. We don't have any sharp corners, cusps, anything like that. No discontinuities. So those three pieces individually would have derivatives. The way they would not have a derivative could be at where they connect. Okay, so if they're not continuous, then they definitely cannot have a derivative there. So we need to check for continuity. So let's check first at x equals 0. Okay, because that's the first place here I want to look. What happens here when x is 0? So at x equals 0, you would have 0 plus 1 squared is supposed to equal 2 times 0 plus 1. So 1 equals 1. That's true. So we know for sure at least it's continuous at x equals 0. That is a true statement. Okay? Then we also need to check at x equals 3 because that's the next place where two pieces go together. So at x equals 3, we would have 2 times 3 plus 1. Does that equal 4 minus 3 squared? That's the question. And we get 7 equals 1, which is not true. 7 does not equal 1. So this is not continuous. At x equals 3, thus not differentiable at x equals 3. Okay? So if it's not continuous, it can't be differentiable. Now, if it's continuous, I just need to verify that the slopes are the same from both sides. Well, I'm just going to have to tell you that they are, because you can't really kind of do that yet. Actually, I guess it's okay because it's at, yeah, because it's 0. So we don't know, you don't know yet how to find the derivative of the top one. So I'm just going to tell you the derivatives are the same. So technically I'd have to make sure the derivatives are the same. So now our question would be, it was called h of x. So h of x is differentiable on minus infinity to 3 union 3 to infinity, because the only place we have a discontinuity or we have a problem is where x equals 3. Now I already explained up here that that's why that's not included, so I don't need to further explain it because I already said that. Okay, let's look at the next example. So it's just talking about piecewise functions. So we've got to have connected and smooth in order for things to work, so we do have to check some things, okay? So let's look at example 6. So here it says, find the values of the constant a where the function is continuous over all reals. So we've done this. So now we're going to add further from what we did previously to make sure we write this with limits. Because if we don't write it with limits, we will not get any credit like on the AP test, okay? So what you want to do is, again, we need to check when x equals 3. Because the only way this graph is not continuous is if one graph stops and the other graph does not start there. Okay, so that's what we need to look at. So when x equals 3, we're going to check what happens. So we're going to have a times 9 minus 3 is supposed to equal 2a. So when we solve this, we would get 7a equals 3, so a equals 3/7. So we know if a is 3/7, this function is continuous. Now, you cannot just say that. So we need to actually show that the limits work. Okay, so we must check okay, and in order to check, we want to know, is the limit as x approaches 3 from the left of this function f, does that question mark equal the limit as x approaches 3 from the right? Okay, so we're going to look. So the limit from the left is going to be the limit as x approaches 3 from the left. So the left side is the top function, and that is now, we know a is 3/7, so 3/7 x squared minus x. Does that in fact equal the limit as x approaches 3 from the right? And the right is the bottom here, and that's 2 times 3/7 or 6/7. So we want to see if they're the same. So question mark, is this limit on the left the same as the limit on the right? So let's plug 3 in. So we get 27 over 7 minus 3, does that again equal 6/7? Because of course the limit of a constant is the constant. So now let's figure out on the left. Well, the left would be 27/7 minus 21/7, because 3 would be 21/7. That's 6/7. 6/7 does equal 6/7. So this is true. Therefore, this function is continuous, and that's the value that works. So this is kind of a star this type question, because to prove continuity, I do need to use those limits. That's really important. Okay, so let's look at this question, example 7. We're going to show algebraically, using the alternative form of the derivative, why g of x is not differentiable. Okay? So what we're going to do is we're going to find the limit as x approaches 1 from the right, and then we're going to find the limit as x approaches 1 from the left. And this is going to be actually, I think I'm going to skip this problem. So let's just skip this one. So just skip example 7, and we're going to skip that. Okay, so we're going to look at what we could do on the calculator to evaluate a derivative. Okay, so to evaluate a derivative, we have some shortcuts and some keystrokes we can do. So let me get a calculator open here. But basically, you're going to do a derivative at a point. Now, I want to caution you to only use a calculator when a question says you can use a calculator. Do not use it when it does not let you do that, because we do need to know how to do the derivatives without a calculator. Okay? So, but we also need to be really good at our calculator when we need it. Okay? Now, you can do the menu thing, but I'm going to tell you we're going to do this a little different. So there's some keystrokes there for the CAS calculator, but I'm going to give you a shortcut. So in order to get this sort of template there, ddx, that I'm doing the derivative, you can actually do that by a shortcut. The shortcut is not on the front of the screen, so you just have to learn it, and it is shift minus. And if I do shift minus, you can see on my screen I have d over d blank. Okay? So I'm going to put x for the bottom, and then inside the parentheses, I'm going to type x squared minus 5x plus 6. Now, outside of the parentheses, if I just do that, it's going to give me a derivative formula. But I want to evaluate this derivative at a very specific point. I want to evaluate it at x equals -3, okay? So we need to put that vertical bar there. Now you can do it by the menu and it'll get you there, but like I said, you're going to use this more often, so I want you to learn this. So you can use this anytime you want to evaluate something at a specific place instead of it just giving you every answer. And in trig, we use this a lot when we're solving trig equations so that we only get the answers on certain intervals. So here, same kind of thing. I want to do the derivative, but I want to evaluate it at only for x equals -3, okay? So what you're going to do is if you look below the control button, you see blue buttons and you see a vertical bar. So you're going to do control of the equal sign, and it's going to give you this little template thing, and you're going to pick the vertical bar. And now you're going to type x equals -3. So x equals -3, make sure you use a negative, not plus, and then you're just going to hit enter. And there you go. There's the derivative evaluated at -3. Okay? So let's talk about how to write that, because we have to be careful that we know how to write everything on our paper, even when we're using the calculator. So what you would do is you would say, I'm doing d dx. They named the function, they called it f of x. So you can just say f of x, or you can type x squared minus 5x plus 6. And then you are going to put down like a subscript. I would prefer you put the vertical bar, but you can say down here x equals -3. So you're literally saying, I'm doing the derivative at -3. And then you just write down what your calculator tells you, okay? Another way to do it would be to find the derivative of x, which is 2x minus 5, and then you could write, I'm doing f prime of -3, and say that it's -11. And then actually you wouldn't even have to do this. You don't have to do that to use this notation, because it literally said find the derivative of that at -3. So if you don't need the formula for the derivative, you can just go right to this. So that's another way to write it, okay? So we'll talk about those things a lot. And remember how important it is for you to be able to follow notation, okay? All right, so let's look at this and let's figure out what happens if you try to do the derivative on the different calculators, or do the derivative on the calculator, okay, and what happens. So I am going to do these because this is really important, and you need to make sure you're practicing with your calculator, because what's going to happen is you're going to get answers when you're not supposed to. Okay, and this is what the caution is always with a calculator, is you need to be sure you understand whether you should get an answer or you should not get an answer. So if we look at A, we're going to do f prime of that derivative. So we're going to do the derivative. So I'm going to do shift minus, and I'm going to put an x there for the independent variable, and in my parentheses I'm going to do absolute value. Make sure you don't use that same vertical bar, because that vertical bar we just used is not absolute value. Absolute value is the little, if you look next to number 9, now it should be red for you, you'll see a template and you pick absolute value, and inside that you write x minus 1. And then we go outside of that and we're going to say evaluated at, so that's control of equal sign, vertical bar, x equals 1, and then we're going to hit enter. Well, it's going to give me the answer plus or minus 1. Well, that's a problem because we can't have more than one answer, okay? And it's using a process and an algorithm, and it doesn't know that you shouldn't get an answer there, okay? But we know that this is not differentiable because this is that graph that we did, right, that has a v here, and we know that right at x equals 1, we do not have a derivative. So this is, again, why I need to know more, and these were the first 3 graphs that we did, right? So we know this is not differentiable. So I need to know more than the calculator. I have to be able to understand that, okay? If we do the next one, so we want to do the derivative of third root of x. So we can do the template. Let me show you something else we can do. We can actually add a page, so control doc, and add a page, and I'm going to add a graph page. And I'm going to graph the third root of x. So control of the caret, the power key, put third root there, x inside, and hit enter. Now, the advantage to this is I now see the graph, so I should be able to tell immediately there's not going to be a derivative at 0 because I'm going to have a vertical tangent line. Okay? But the other thing I've just done is I've just stored that function and called it f1. So now I can go back to my calculator page and I can actually tell it to do the derivative of f of 1 at 0. So I can do my shift minus, pick an x there. Inside here, instead of just doing, oh, I don't know why that picked a big X, hang on. Let me get rid of that. Should just be a lowercase x. So I'm going to just use f1 of x, but I'm going to do f1 of 0. Okay. So since I basically just stored it and it was called f1. Notice that it turns bold. That means that's defined. That's been saved. And then I'm going to put parentheses 0. So now I'm telling it to do the derivative of the function I stored called f1, and I'm doing it at 0. Well, it tells me 0. Well, we know that that's not true. Oh, actually, sorry. It's not. I can't do it that way. I just realized what I just did. So let me go up here and copy. So if you don't know how to do that, highlight and copy. I can't do f1 of 0. Sorry. I have to do, because that's a constant. So, of course, my derivative is 0. I still have to do f1 of x. And then I still have to do control, get my vertical bar, and say x equals 0. Okay, and then I hit enter, and it says undefined. Okay, different calculators will actually give an answer. Okay, and so again, that's why I have to know more than that. So I'm not going to do the last one. I'll let you do C on your calculator, and then we'll finish and we'll do example 10 as a nice review of all of the stuff that we talked about. So we'll do that part in class.